Welcome back! Today we are shifting gears from the AWS console to the realm of developers. Get ready to master command line interactions and Boto3 essentials for Amazon Bedrock. As we mature in our generative AI journey, relying solely on web-based playgrounds is no longer sufficient. While the Amazon Bedrock console is a fantastic environment for rapid experimentation and visual testing, building scalable, enterprise-grade applications requires strict programmatic access. We must transition from clicking buttons to executing code. What tools does AWS provide to facilitate this leap? AWS equips developers with two primary mechanisms for interacting with the Bedrock API: the AWS Command Line Interface, or CLI, and the AWS Software Development Kits, known as SDKs. Serious? The AWS CLI is a unified tool that allows you to control multiple AWS services directly from your terminal. It is exceptionally powerful for scripting quick infrastructure tasks, testing model availability, or executing rapid one-off inferences without writing a full application. Amazed. However, when you are ready to build dynamic, multi-turn conversational agents or complex retrieval augmented generation pipelines, you will leverage the AWS SDKs. Very fast? AWS provides SDKs for various programming languages, such as JavaScript, Python, Java, and more. These SDKs provide wrapper libraries that make it easy to integrate Bedrock API calls into your code. Long pause. In the data science and AI community, Python reigns supreme. Therefore, we will focus laser-tight on mastering Boto3, the official AWS SDK for Python. Let us fire up our terminals. This flowchart illustrates the transition of developer tools. While beginners rely on the AWS Management Console, advanced developers route their workflows through the AWS CLI terminal and AWS SDKs like Boto3 to achieve fully automated and programmatic access to the Bedrock API. Before we write Python code, let us demonstrate the raw power of the AWS CLI. Once you have installed and configured the AWS CLI on your local machine with your secure IAM credentials, you have direct command line access to the entire Bedrock ecosystem. How do we prompt a massive foundational model from a simple terminal window? We utilize the Bedrock Runtime service command, specifically targeting the invoke model operation. You must carefully construct your command. You specify the --model ID to target the exact model you want, such as Mistral 7B. Then you pass the --body parameter as an escaped JSON string containing your prompt and inference configuration. It is incredibly fast and efficient. However, terminal environments can sometimes struggle with raw binary or complex text outputs. To mitigate this, AWS provides specialized formatting flags. By appending --CLI-binary-format raw in base64-out, you instruct the CLI to safely encode the payload, ensuring the model's response is cleanly captured and written directly to a specified output text file on your local disk. Let us examine the exact syntax of this powerful CLI command. Let us break down this terminal command. We initiate the call with AWS Bedrock Runtime invoke model. We set the --model ID flag precisely to the Mistral 7B instruct model. The --body flag is where it gets tricky. Because we are in a terminal, we must escape the JSON quotes. We pass the prompt meticulously wrapped in the inst tags required by Mistral and set max tokens to 200. Finally, we apply the --CLI-binary-format flag and direct the entire generated response to be saved locally into a file named output.txt. Trace the CLI execution path. The terminal command packages the model ID flag and the JSON escaped body. This is processed by the AWS CLI engine, securely dispatched to the Amazon Bedrock runtime, and the final generation is written directly into the local output.txt file. Now, let us transition into writing actual application code using Python and Boto3. But first, a critical architectural concept. Like other AWS services, Amazon Bedrock provides several APIs. These APIs can be placed under the Control Plane API for managing, training, and deploying FMs, and the Runtime Plane API for making invocations or inference requests to the FMs. Why does AWS split the service into two distinct planes? It is for robust security, scalability, and operational isolation. The control plane, accessed in Boto3 via the Bedrock client, handles administrative tasks. This includes listing available models, retrieving model metadata, configuring guardrails, or kicking off a massive multi-day model fine-tuning job. These operations are low frequency but high impact. Conversely, the data plane, accessed via the Bedrock Runtime client, is your high-speed inference engine. This plane is relentlessly optimized for low-latency, high-throughput execution. When your application needs to send a prompt and receive a token stream in milliseconds, it talks exclusively to the data plane. Understanding this separation is mandatory. If you try to invoke a model using the control plane client, Boto3 will instantly throw an error. Let us dive into the control plane APIs to discover the models available to us. This architectural diagram demystifies the Bedrock API planes. The Boto3 SDK routes administrative tasks to the control plane client named Bedrock, managing models and fine-tuning. High-speed inference tasks are strictly routed to the data plane client named Bedrock Runtime. To utilize the generative capabilities of Bedrock, the first step is to discover which FMs are available via the service. You cannot invoke a model if you do not know its exact system-recognized identifier. The generative AI landscape evolves rapidly, and AWS frequently adds new models or deprecates older versions. How do we dynamically query the platform to see what is currently active? We utilize the control plane API, specifically the list foundation models operation. Excitedly, by invoking this API, Bedrock returns a comprehensive metadata payload containing every base model your account has access to. It retrieves metadata about the base models, including the unique model ID required to generate content using that model. Very fast. The payload includes crucial details like the provider name, the input modalities, whether it accepts text or images, the output modalities, and most importantly, the exact model ID string. Amazed. You must extract this model ID string because you will use it as a mandatory parameter when you eventually switch over to the data plane to perform your inference. The payload includes crucial details like the provider name, the input modalities, whether it accepts text or images, the output modalities, and most importantly, the exact model ID string. You must extract this model ID string because you will use it as a mandatory parameter when you eventually switch over to the data plane to perform your inference. Let us look at the Boto3 Python syntax required to establish our client and pull this vital registry of models. Exciting the simplicity of Boto3 initialization. We import the Boto3 library and call boto3.client. Crucially, we set service name equals Bedrock to explicitly target the control plane and specify our region. We then execute the list foundation models method. The AWS SDK handles the network request and returns a rich Python dictionary. By accessing the model summaries array inside the response, we can iterate through the models and dynamically extract the exact model ID strings needed for our downstream applications. The programmatic discovery flow is highly linear. We initialize the Bedrock client, execute the list foundation API against the AWS control plane, and receive a rich metadata dictionary from which we programmatically extract the model ID string.
Sometimes simply knowing the model ID is not enough. When building highly dynamic enterprise applications, your code might need to programmatically verify a model's exact capabilities before attempting to use it. For instance, what if your application suddenly requires image generation, but the model ID passed to it is strictly a text-to-text model? An invocation would fail instantly and crash your application. To prevent this, utilizing Amazon Bedrock, developers can access state-of-the-art generative AI models through the Get Foundation Model API call.
This operation retrieves comprehensive information on a specified base model. By passing a specific model ID to this control plane API, Bedrock returns a highly detailed specification sheet. You can programmatically check if the response streaming supported Boolean is true, or verify the exact custom model customization techniques supported. Very fast, this allows you to build deeply resilient AI pipelines that self-validate the models they are assigned, failing gracefully or routing to alternative models if the required capabilities are not met. It is defensive programming tailored for the generative AI era. Let us see this API call in action. Let us inspect this validation logic. Once again, we utilize the Bedrock control plane client. This time, we execute the getFoundationModel method. Notice that we must explicitly pass the model identifier parameter. In this example, we pass the exact string from Meta's Llama 3 70B instruct model. The response payload contains a model details object, populated with critical booleans and metadata, allowing our application logic to securely verify the model's architectural capabilities before ever attempting a live inference. This flowchart demonstrates defensive AI programming. The application logic passes a target model ID to the getFoundationModel API. The returned detailed spec sheet is evaluated. If capabilities are met, we proceed to inference. If not, we execute a graceful fallback.
We have discovered our models and validated their capabilities. It is finally time to generate. We are leaving the administrative control plane and plunging into the high-speed data plane. You can invoke specified Bedrock models to perform inference using inputs provided in the request body. The Invoke Model API allows you to run inference for various model types, including text, embedding, and image models. To do this, you must meticulously construct your API request. First, initialize the Bedrock Runtime client. Then, you must build a Python dictionary containing your exact prompt and inference parameters, such as temperature and max tokens. Crucially, because Boto3 expects the body to be a raw byte stream or a JSON string, you must use Python's json.dumps method to serialize your dictionary into a properly formatted JSON payload. You then call the invoke model method, passing your serialized body, your target model ID, and strictly setting both the accept and content type headers to application/JSON. The Bedrock runtime ingests the payload, executes the massive neural network calculations on AWS GPU clusters, and returns the generated tokens. Let us review the exact Boto3 code required to execute this inference end-to-end. Let us trace this complete inference execution. We define our target model ID and our string prompt data. We then serialize our configuration into a JSON string called payload. Critically, we instantiate the Bedrock runtime client. We pass our payload into invoke model alongside the necessary MIME type headers. The response object contains a raw byte stream under the body key. We read the stream, parse it back into a Python dictionary using json.loads, and finally extract the magnificent generated text. This is the core execution pipeline. The prompt and config are serialized into a JSON payload. This is fired through the invoke model API to the data plane. The returning byte stream response is mathematically parsed back into a dictionary to extract the generated text. As we wrap up our mastery of Boto3 essentials, we must discuss the most critical aspect of production readiness: authentication and security. In our simple code examples, you might have noticed we did not hardcode any AWS access keys. Hard-coding credentials in your scripts is a massive security vulnerability. So, how did Boto3 know who we were? The Boto3 SDK automatically searches your local environment for credentials, typically configured via the AWS CLI or attached directly to your EC2 instance or Lambda function execution roles. In an enterprise environment, you will rarely use long-term access keys. Instead, your application will assume highly restrictive IAM roles, generating temporary, short-lived security tokens via the AWS Security Token Service, or STS. You can use Boto3 to dynamically assume these roles, inject the temporary credentials into a persistent Boto3 session object, and construct your Bedrock clients from that secure session.
This guarantees that your generative AI applications adhere to the absolute highest standards of cloud security and the principle of least privilege. Master these Boto3 mechanics, and you control the full power of Amazon Bedrock. We invite learners to like, subscribe, and visit quicktechie.com for premium and for recently updated material as per latest syllabus and certification prep, Q&A banks, ebooks, audiobooks, full training, interview guides. On YouTube, it may not be a latest contents. Observe the secure authentication pathway. On application startup, we request temporary credentials via STS to assume a restricted IAM role. This secures a Boto3 session to initialize the Bedrock Runtime client, ensuring secure, least privilege inferences every time.